Hello and welcome. My name is Mike Price. We are still talking about functions, section 1.1. We have our fourth objective to discuss. That is form and use composite functions in applied problems. We'll find our example here. So, function composition. This is kind of a challenge. If you recall this, it's entirely possible that you talked about this in a Math 111, a college algebra course as a prerequisite. And what makes composition so hard is that there are lots of things that we can do with functions that we can also do with numbers. For example, you can add two numbers together, you can multiply two numbers. You can do the same thing with functions. You can add two functions together, you can multiply two functions. What you can do with a function that you cannot do with a number, one example is compose them. So this is putting two functions together. If we go back to our factory or kind of machinery example, function composition is basically one conveyor belt, but with two different machines that get to do stuff to that input. So as a kind of tacky example, you might consider yogurt. So you got those little yogurt cups. You imagine an empty one going through one machine, and the first machine squirts the yogurt into the cup. It continues down the conveyor belt. The next machine puts the cap on it. So there's two distinct functions that occur here, and the end result is a closed, sealed container filled with yogurt. So, of course, it can't be that easy because this is math, but when we try to consider this with function notation, maybe you can keep going back to that in your head. So our definition is given two functions f and g, composite function is defined to be, well, we use this little circle-y thing. This is usually just read as of. You could also read it as composed with. One cute way I like to think about it is eating. So this is f is eating g. And that's because if you notice, g becomes the input to f. So this is just to reinforce that kind of machine idea. So we start with some input, it rolls through here. Here may be the yogurt squirting machine, and then we've got output. Then that becomes input again. You take that cup that's filled with yogurt, and then you put it through the sealing machine. So now it's got the cap on it, and your final output is the f of g of x. So it takes x, puts it in the g function, and then takes that result into f. So a mathematical example, we'll get ourselves two nice functions. One of them, f is x squared, g is 2x plus 1. And then let's take the composite function f of g. And maybe to make it easier, let's start with a concrete number. So we'll pull -2 out of this instead of using just plain old x. So just using the definition of function composition, this says f of g of -2. I really think color is pretty useful for this stuff. So I'd like to think of this inside as one distinct chunk. So f of g of -2 gets the whole deal, but g of -2 is really where I need to focus to get anywhere right now. So g of -2 is really all of this. So take a look up at our function. Here's g of x. So for any input x, it's 2 times that input plus 1. Well, g is just getting evaluated at -2. So instead of having an x here, now we have -2. That's all that's happened. The most complicated part is that this is tucked inside of f. Let's just ignore that for the moment. It's certainly part of this problem, but for right now, all we need to do is tidy up this inside. 2 times -2 is -4. 1 greater than that is -3. So really, g of -2 is -3. In that conveyor belt example, what we've accomplished so far is putting the first number into the first function. So it's made it through the first machine. Now we still have f of -3 left. We still have that second machine to go through. So our revised input, our yogurt cup, which is filled with yogurt but not yet have a cap on it, is -3. So now we're going to take that and put it into our final function. So f of something looks like that thing squared. So in this case, we've got f of -3. So -3 needs to all get squared. Parentheses, as you might notice, are very important here. So we've got -3 all squared, and that leaves us with just 9. So there's our yogurt cup that's sealed and filled with yogurt. Yum, now I'm hungry. Okay, so to get to an example that's more in line with our business and economics goals here, we've got one that we'll have to bear with me, just keep a little track of. So we've got demand for a product, and instead of being in terms of the price or the products, instead of terms of its price, we've got demand in terms of time. So this is how many units will be sold T months after its release. And then advertising budget, which on the surface seems unrelated, but it's in terms of demand. So the input to this advertising function is demand. That's 5 minus the square root of the demand, number of items in thousands that are demanded. So the question is, how much is spent on advertising 6 months after the product's release? So we need to get from math to English, which is one of the hardest things we will have to do, but unfortunately it's also one of the most important. There are lots of programs that can compute all this stuff for us. There are not a lot of programs that translate English into math very well. Okay, how much is spent on advertising? Well, so that's the first part of our question. That really is just our function, A of D. A gives us amount of advertising as a function of demand. 6 months after the product's release is a time. That tells us that T is equal to 6 because our time T is in months. And then A of D would be, we need to evaluate that with T is equal to 6, which you might notice this is sort of a challenge right off the bat because there are no T's in this. But recall that we've got a way to get between T and D. So the thing to realize is that demand, D, depends on T. We need to grab that function, D, that we were given earlier on and replace it in this A function. So here's D, just fancying it up, putting a little tuxedo on it, D of T instead of just little d. But D of T is just this function, 10 minus T. So now what we've got is A of this expression. And A of this expression, if we look back at our original function for A, so A is just 5 minus the square root of something, whatever our input is. So 5 minus the square root of, well, we want 10 minus T. So 5 minus the square root of 10 minus T. We're not totally done yet. That's our function of, advertising is a function of time. And if you recall, what we really need to do is evaluate this at T equals 6. So all put together, we have A of D of 6, there's our time, 5 minus the square root of 10 minus 6. Okay, 10 minus 6 is 4. We can do this. And so the square root of 4 would be just 2. 5 minus 2 is 3. And then it's always polite, this was phrased in terms of words, so we should return to words before we're done. So after 6 months, $3,000 is being spent on advertising. We're paying attention to units. T was in months, so T equals 6 means 6 months. And our output advertising was in thousands of dollars, so this is $3,000 being spent on advertising. Okay, that wraps up all 4 learning objectives for section 1.1. We'll come back with more in section 1.2 in the next video. Thank you.